Okay, hi everyone. We're talking about the variational principle as one does on a Friday. I introduced it in the previous video, and remember that the variational principle is essentially a guess and check type method. It allows us to calculate an upper bound to the energy, but the penalty is that we don't know how close the calculated energy is to the true one. And what I really want to talk about in this video is how can we be as clever as possible with our guesses to get the best possible answer? And here's how that works. There are essentially 4 steps. So the first step is to guess a form for the wave function, which is a function of one or more adjustable parameters. This part in red here, the idea that we're going to add an adjustable parameter to the wave function is the new and important idea. Right? I'm going to call this parameter a variational parameter. We'll give it the symbol alpha or beta. And essentially this allows or provides us with some flexibility in our wave function to find the best form of it for our problem. Once I have the wave function, I'm going to calculate energy as a function of the adjustable parameter. So I will get an equation. E is a function of alpha, beta, whatever. Once I have that equation, I will find the value of alpha or beta that minimizes energy. Recall from your calculus that in order to find the maximum or minimum of a function, you take a derivative. So that's kind of where we're headed. Once I have those values of alpha or beta that minimize my function, I can plug them back into my energy equation and determine E min. So those are the 4 basic steps. And if that all seems a little bit abstract, that's okay. I'm going to walk you through an example. Step 1, guess the form for the wave function, which is a function of one or more adjustable parameters. Previously, we talked about a particle in a box, and we had imagined guessing a wave function which looks like this, right? A quadratic function. But I could just have easily guessed some other type of polynomial, right? I could have guessed x squared times L minus x squared, or x cubed, or x to the 1/2. There's nothing which says that it has to be an integer, right? Maybe the squared is better, maybe the cube, maybe the 0.5. We don't know. And in general, I could write any one of these functions in the following form. Right? Phi is equal to x to the k times L minus x to the k, where k is just some number. In this function, it is k, which is my variational parameter. And what I'm going to do is adjust this function, adjust the value of k to find its value, which minimizes the energy. Second step, calculate energy as a function of your variational parameter. Here's my trial function with my variational parameter k. This is my formalism for calculating energy. I introduced this in the last video. And I'm just going to walk you through a little bit of this. One of the first things that you're going to have to do is calculate a Hamiltonian operating on phi. That will look something like this, negative h bar squared times the second derivative of this function. Remember that k is just a number. It could be 1, it could be 2, it could be whatever. And so when I start to take the derivative of this again is a product rule. If k is a number, I take the derivative of the first, the k comes down, and I get x to the k minus 1. Leave the second constant. Plus, leave the first one constant and take the derivative of the second. Right? So the k comes down, and I get L minus x to the k minus 1 times the derivative of what's inside. Right? That's the negative 1. You could factor off some common terms. Factoring things often makes your life very easy. So you could recognize that you could factor off an x to the k and an L minus x to the k, and you get an equation that looks like this. And then to make your life even easier, you might recognize that this function here, x to the k, L minus x to the k, is again our original function f. So I can write that first derivative in this way. I then have to take a second derivative. And again, this is a product rule, right? F is a function of x. So derivative of the first is f prime times leave the second one constant plus leave the first one constant and then take the derivative of the second. And that looks like this. We could go on, but I think you're getting a sense of this. Right? The calculus that is involved is pretty detailed. And we're not even done. So once I take this second derivative, I've got to multiply this by phi star and then integrate it over all space. And that's just the numerator. You have to do the same thing with the denominator and put it all together. So there's a lot of calculus involved in all this, but it can be done. And if you were to do it in this specific problem and put it all together, the energy that you calculate is given by this expression, h bar squared over ml squared times 4k squared plus k over 2k minus 1. This is our final answer. We have now calculated our energy as a function of our variational parameter k. One pro tip, I mentioned that the calculus can be pretty rigorous. This is a place where computational software, specifically Mathematica, can be really, really helpful. So if you're not familiar with using it, this might be a really, really good time to familiarize yourself. Step 3, find the value of alpha and beta that minimizes the energy. And here we go. This was my energy equation. This equation describes how the energy depends on the adjustable parameter k. At the minima or maximum of the function, the derivative of it with respect to k is equal to 0. So I have to take the derivative of this with respect to k. Again, this is a quotient rule, and I never remember the quotient rule. I just think of this as a product rule. So I could write this in the same way as 4k squared plus k times 2k to the minus 1 all to the negative 1. Take the derivative of the first, 8k plus 1, times leave the second one constant. Leave the first term constant and take the derivative of the second. So the minus 1 comes down. I get 2k minus 1 to the minus 2 times the derivative of what's inside. It's equal to 2. I want to factor off as much as I possibly can. That gives me 2k minus 1. I could factor that off of both terms. And I'm left with this. In order to find the value of k, which minimizes this, I'm going to set it equal to 0. And I could take any one of these functions and make them equal to 0. If you think about this one value of k would be k equals infinity. K equals infinity, this would go to 0. Or alternatively, I can take the inside of all of this and set it equal to 0. I think this is all that same thing. I had an extra slide in there, I apologize. So what I was suggesting was that I could take any one of these values or take this polynomial and set it equal to 0, and I will find the value of k, which minimizes the function. So that's written here. Working through this, I bring this term over to the right-hand side. I cross multiply things and you end up getting a quadratic. You solve this for k, and here's our final answer. K is equal to 1.11 or negative 0.112. We have found the values of alpha and beta that minimize E. Last but not least, I am going to plug those values back into my energy equation to determine E min. Here's my energy equation. It's a function of k. This was my value of k, which minimized it. If I plug in k equals 1.11, I end up getting 4.95 h bar squared over ml squared. And again, if you go through and you were to compare that value to the true value, you will find that the energy that's associated with this trial function is only 0.3% bigger than the true energy. So we didn't solve anything. We just did a bunch of calculus with a guessed function, and we got our answer right within 3 parts in 1,000. Pretty good. This is what those functions look like. So again, the dashed blue line is the true answer. The red line is what we started by guessing. And if we use the variational theory to find the value of K, which optimizes it, you get the green curve, which is looking very, very close to the true answer. So in summary, we have two types of approximation methods. Perturbation theory. Perturbation theory requires us to know something about the solutions before we start, right? And because we know something about the solutions, we know that the calculated answer is somewhat close to the true value. Variational theory is a complement to this. It can be used in any situation. We don't need to know anything about the answers ahead of time. But the penalty you pay is that you don't know how close your answer is to the true answer. And the quality of your result depends on how well you guess. So both of those techniques are going to be very useful moving forward, and we will talk about them in the context of a number of different problems. At this point, I would recommend that you complete the worksheet problems on the approximation methods and let me know if you have any questions. See you soon.